Every time a new space telescope has been launched, it has uncovered something completely unexpected. When it comes to complexity and size, NASA has never launched a space telescope quite like the James Webb Space Telescope. Telescopes are like portals to the past. Webb will force us to return to the era of the earliest stars and galaxies. To look as far back in time as possible, when the cosmos was perhaps 100 million years old. The Webb telescope was built to investigate planet atmospheres. We've assembled a set of cutting-edge tools. The James Webb Space Telescope will be an invaluable tool in the future search for life. Welcome to the Space Dynamic YouTube channel. In this video, we will first go over the photographs and briefly examine them. Then, we will quickly go through JWST, its importance, and how it operates. Finally, we will explore how the improved capabilities of the Webb compared to the venerable Hubble Space Telescope will affect research in the future. So before starting this video, like this video and subscribe to our YouTube channel for future updates. The first science image from the James Webb Space Telescope was released to the public on July 11, 2022, making history. As soon as it was made public, it surpassed the previous record for the universe's deepest vision. A remarkable accomplishment. This record was formerly held by the Hubble Space Telescope, which was initially established in the middle of the 1990s with the initial Hubble Deep Field and repeatedly beat it throughout time. But you can see how much more information Webb's sensor is able to capture by contrasting its initial image with related ones acquired by Hubble of the same section of sky. What, then, can we actually make out in this fresh deep field picture? How much more of the universe does it expose, then? Prior to starting the image comparison. The capabilities of the telescopes are not identical, therefore let's begin with a general summary of their differences. Webb is commonly referred to as Hubble's replacement, although NASA prefers to describe to it as its successor. Webb will largely examine the universe in the infrared, whereas Hubble focuses on optical and ultraviolet wavelengths, but it also has infrared capabilities. Webb and Hubble are both reflecting telescopes that function conceptually. The same light bounces off a big primary mirror onto a secondary mirror, which redirects it to science instruments for analysis. Hubble's mirror is 2.4 meters wide, or 7.9 feet wide, whereas Webb's segmented honeycomb-shaped mirror is a massive 6.5 meters wide, or 21.35 feet wide. Webb has the largest ever flown mirror in space. Its 18 lightweight beryllium segments are coated with a small layer of gold, making it significantly more sensitive to infrared light and allowing it to see further back in time than Hubble ever could. Additionally, the two telescopes have extremely distinct cooling requirements and occupy quite distinct positions. Hubble orbits the Earth, while Webb observes the universe from a distance of 1.5 million kilometers, or roughly 1 million miles, at a place known as the second Lagrange point. Now we have a better understanding of how each telescope differs. Let's investigate the photographs. This was the first deep field, and while we are all familiar with Hubble's, there was also the original deep field and an ultra-deep field. However, one of the major claims made for JWST was that it will be able to view deeper back into the cosmos than ever before. Hubble and many of these galaxies were simply very red, but on JWST they were able to draw it in somewhat. Naturally, they colorize it, but due to its near-infrared vision capability, it was able to see considerably further and clearly on these objects. When you look at this, the first thing that strikes you is the amazing clarity when you zoom in. Which means that even millions of light years away, perhaps as far as 13.9 billion light years, you can still distinguish individual stars in these galaxies. You can see all these anomalies in the strange curves of these galaxies, and some of them over here are completely curved. Of course, gravitational lensing is to blame for this. Because of the high gravity being created right there in the middle by the gravitational lensing in that galaxy cluster, you can see a galaxy cluster in the middle and how everything is kind of curling around it. Firstly, as Neil deGrasse Tyson was saying, you can just ignore those stars up there because they are actually stars in our own Milky Way and are therefore in front of all the galaxies behind it. As a result, they flare out like that, and the reason they do so in 6 points is because all of the mirrors on JWST are hexagonal. As a result, you will receive 6 points from them, and this will serve as one of JWST's defining characteristics. So this one is a bit of a jaw-dropper. It's called the Southern Ring, and it's a dying star surrounded by layers of gas and dust. The different layers correspond to different episodes of the star throwing off its gas and dust, etc. So the various layers indicate that this has been going on for a long time, but the detail in the ring is quite intricate. But what's really cool about this is that they use two different instruments, one of which is the near-cam, which is the near-infrared, which is a lower wavelength of infrared, and the other is the MIRI camera, which is the mid-infrared, and the difference between the two is that the MIRI camera picks up more dust, so you can see those large dust clouds and other such things. This one passes through the dust a bit more, but what they were able to see is that it's actually a binary system, so this tiny star on the side is the one that erupted and sent out all the gas and dust, and it's rotating around, or they're revolving around this larger star. It's a binary system, which you couldn't really see on this or any other, although you can kind of see it right there. However, this was the first time that has been picked up, so once more it's just kind of demonstrating the power of the various instruments on the Webb, but mostly it's impressive when you look at a comparison between this and Hubble. Now that the JWST is orbiting a fourth time further away, I'm going to show you the most dramatic image so far. The Carina Nebula is 7,500 light-years from Earth, and this small portion of it is just barely visible in this picture. This is not a typical nebula. Nebulas consist mainly of gas and dust, but this one's actively forming new stars. It's one of the most active star-forming regions in our galaxy and can provide us with a lot of information about how stars form. This image is around 16 light-years wide and a spectacular sight. It's being called the cosmic cliffs by astronomers. Massive young stars just out of frame bombard this region with cosmic radiation that chips away the dense wall of gas. Hot ionized gas streams into the blue area here, where it is heated and fluoresces. I just wanted to mention that all the bright points of light you see on the Webb will have these 8-pointed stars, 6 big points like a snow-striped star and 2 smaller horizontal zigzag lines. These are diffraction spikes. As cool as they are, they're not a problem for astronomers. They can rotate their telescope so that the spikes won't obstruct the view of anything interesting. Nevertheless, they're still worth checking out and will always be a sign that an image comes from the Webb. We then go here to the NIRCam image, but we can now switch over to a smaller image that's a composite of MIRI and NIRCam. This is an amazing example of how using mid-IR to see through dust allows us to see what's underneath. Hubble has been photographing this area for some time now. Now you can see the transition from Hubble's imagery, through the near-camera MIR website composite photo to a pure NIRCam shot. This image is just so pleasing to my eyes. Now's the time too, we can finally leave our galaxy. Sheer far out from 7,500 light-years away to 300 million light-years away and see Stefan Boltzmann's quintet. This photo is of 4 galaxies in the local group, which are all very close together. The one on the left is only 40 million light-years from Earth and happens to be in this picture, too. But those 4 galaxies are the tightest galaxy grouping we've ever discovered. 2 of them are in the process of merging and all 4 of them will merge eventually. This is the largest of JWST's first images, a composite of over 10 images. When all added up, it is 150 million pixels. Zooming in on any part of this picture and you can see not just the 5 galaxies, but literally hundreds more. The picture's predecessor is a mid-infrared image which resembles a mirror. Right at the beginning, there's one thing that stands out. That brightest object in the uppermost galaxy is actually a supermassive black hole with a mass 24 million times its size, and it's actively swallowing more material and emitting more energy. This image shown here by Hubble is transitioning from the original to the mirrored and finally to the cam mirror.